Okay, so let us try to understand how to draw the shear force and bending moment diagram in case of a simply supported beam carrying UL and a point load. So as shown over here, we are having a simply supported beam of span 7 meter and it carries a UL of 2 kN per meter at a distance of 4 meter from the left hand support. And similarly, we are having a point load of 5 kN acting at a distance of 2 meter from the right hand support. The first step is to find out the reactions Ra and Rb. So here, this is the UL 2 kN per meter. The meaning of this is that for 1 meter length, the load that is acting is 2 kN, and here there is a 4 meter length, and therefore the total UL will be equal to 2 multiplied by 4. Because for 1 meter length, the load is 2 kN. Then for 4 meter, it will be 2 into 4 kN. So that is indicated over here, and allow it to act at the center of the length over which this UL is acting. So UL is acting over 4 meter length. So this particular, we have converted this UL into point load and allow it to act at the center of this 4 meter length, that is 2 meter, as shown over here. Now we'll apply the conditions of equilibrium. So the first condition of equilibrium is that the summation of the forces in y direction is equal to 0, and assuming that the upward force is positive and downward force is negative. So Ra, it is acting in the upward direction. Rb, it is also acting in the upward direction. 2 into 4 kN, that is the UL load that is acting in the downward direction, and this 5 kN, it is acting in the downward direction. So Ra plus Rb minus these two loads, they are negative because they are acting in the negative direction. So therefore Ra plus Rb is equal to 30 kN. Now we'll take the moment about A. So summation of moment about A is equal to 0. That is the second condition of the equilibrium. Considering clockwise moments positive and anti-clockwise moments negative. So we can start with this particular Rb. So Rb will have a moment of, it will have, if you see this particular, it is having anti-clockwise moment. So therefore that is negative. And what is the perpendicular distance from B up to point A is 7. So that is 2 plus 1 plus 4, that is 7. So minus Rb into 7, that is our first term. This 2 into 4, that is the UL load, will have a clockwise moment as shown over here. And the perpendicular distance from this point up to point A is 2 meter. So it is 2 into 4 into 2. But as it is clockwise, we have considered this as positive. Similarly, this 5 kN force point load will also have the clockwise moment about point A, and the distance from C up to point A is 4 plus 1, that is 5. This is 1 meter, this is 4 meter, so 4 plus 1, that is 5 meter. So, and as it is a clockwise, that will be 5 multiplied by 5, and that is equal to 0. Transfer this negative term on this side, it will become positive, and if we simplify, we will get reaction at point B is equal to 5.86 kN. Now we can substitute this value of reaction at B in this equation. So substituting this value in the equation 1, we will get Ra is equal to 13 minus Rb, that is 13 minus 5.86, that is 7.14 kN. So we have obtained the reactions at A as well as reaction at B. Now you see how to draw the shear force diagram for this. So as you can see over here, shear force at point A is nothing but what is the reaction, that is Ra, and as it is acting in the upward direction as per the conventions, the forces which are acting in the upward directions are positive, and the forces which are acting in the downward direction, they are considered as negative forces. So shear force at point A, it is acting in the upward direction, that is the reaction Ra is in upward direction, so it is positive, that is 7.14 kN. Shear force just at the left of the C will have this Ra, that is 7.14 acting in the upward direction, minus this UL of 2 into 4. So that is 7.14 minus 8, that is minus 0.86 kN. So at point A, we are having 7.14 kN, whereas at the C left, we are having minus 0.86 kN. Exactly at C also, as there is no other point load or there is no other load, we can say that whatever the shear force is there at C level, the same shear force will be acting at point C also, and that is minus 0.86 kN. From C up to D left, there is no other force that is acting. So whatever the force that is acting at the C left, or rather at C, the same force will be acting at D left also. So that is also 0.86 kN. So that also we have indicated over here. But suddenly at point D is a downward acting point load. So minus 0.86 minus 5, so that will be minus 5.86 kN. That will be the shear force that is acting at point D. From D up to B left, there is no other force that is acting. So whatever is the shear force that is acting at D, the same will be acting at B left also. So that is minus 5.86 kN as shown over here. But suddenly at point B, there is a point load of 5.86 kN but acting in the upward direction. So minus 5.86 plus 5.86, because this is acting in the upward direction, that will be 0. That will close the shear force diagram. So it must be a closed diagram. Now here you can see this is the point at which the shear force is becoming 0. So we have to locate this particular point from A, or you can say from left hand support. And the point at which the shear force is 0, we will always find that the bending moment is maximum. So first we'll locate this point A. We'll locate this point from the A. So suppose we take into consideration this distance as x from A. So now as we have seen that this is 4 meter and we have assumed that this distance is x meter. So naturally this remaining distance will be 4.x meter. So, and now you can see these are the two similar triangles that they have formed over here. For example, this A, E and this particular triangle, and here it is EC and this particular triangle. So this is one similar triangle that we have obtained, that is this particular triangle. This is one triangle and this is another similar triangle. So we can apply the principle of similarity over here. So we can say that the height of this larger triangle is what is 7.14 divided by its base. Base is what it is x, will be equal to the height of the smaller triangle is what it is 0.86. So this is the height of the smaller triangle, that is this particular triangle. So we are taking into consideration this smaller triangle, this particular triangle into consideration, and then this larger triangle into consideration. So as you can see that in this particular case, the height of this larger triangle is what is 7.14 and its base is x. So it is 7.14 divided by x. The height of the smaller triangle is this one, that is 0.86 divided by its base, that is 4 minus x. So we have applied the condition of the similarity of the triangles, and if you cross multiply this, so you can cross multiply these particular terms. So 7.14 into 4 minus x will be equal to 0.86 into x. And now you can multiply by this 7.14 inside the bracket. So 7.14 into 4 and 7.14 into x. And if you rearrange the terms, then you will get the value of x is equal to 3.57 meter from A. So at a distance of 3.57 meter from A, the shear force is 0. And at this particular point, we can first find out what is the bending moment, because the bending moment at this particular point will be always maximum. So we'll just extrapolate this particular onto our main diagram. So this distance is x and this distance is x, and we know that the UDL is 2, so it's 2 into x is the UDL load, and this 2 into x, which is the UDL load, we convert it into point load by allowing it at the center of this distance x. So x by 2 and x by 2, that is the center. This is the center point of this particular distance x. And now we can take the moment about this particular section, that is this section under consideration at a length of x from the A point. So if you consider this section and if you want to find out the moment about this particular section, then you have to start with this RA. So RA will produce the clockwise moment about this section. So it is RA and perpendicular distance from point A up to this section is x. So it is RA into x, and as it is positive, as it is clockwise, it is positive. So that is RA into x. And this UDL, which we have converted into point load, that's 2 into x, it is acting in the downward direction and it will produce the anti-clockwise moment about this section. So it is negative. So 2x is the load and perpendicular distance is x by 2. So 2x into x by 2 that we have shown over here. So this 2 and this 2 will get cancelled. So this ultimately RA into x minus x by. Substitute the value of RA. RA is 7.14 and value of x that we have already calculated is 3.57 and x is 3.57 and square of that. So we get this as the maximum bending moment for this particular arrangement. Now we go for the bending moment calculator. Now, as we know that in case of the simply supported beam, the moment at the end points is always 0. So bending moment at point A is 0. Maximum bending moment will be at a distance x, that is 3.57 meter from A, and that already we have calculated previously. So these two values we know. Now we have to calculate bending moment at point C, okay, using the same concept as we have done earlier. So start with RA. RA will produce the clockwise moment about point C. So therefore it is positive. So RA into the perpendicular distance from A to C is 4 meter. So RA into 4 is the clockwise moment that we have indicated over here. This UDL load 2 into 4 and it is acting at the center of this 4 meter, that is 2 meter. It will produce the anti-clockwise moment about this particular point, that is C. So it will be negative. So 2 into 4 is the load and 2 meter is the distance. So that is negative because it is anti-clockwise. So we get this particular value, that is 12.56 kilometer. Similarly, bending moment at D. Again, we have to start from RA. This RA will produce a clockwise moment about point D, and the perpendicular distance is 4 plus 1, that is 5. So it is RA into 5. This particular UDL is 2 into 4 and it is acting at a distance of 2 meter, that is the center of 4 meter length, but it will have a distance of, we have to take moment about point C. So from this point up to this point, the total distance is what? 2 plus 1, that is 3 meter. So 2 into 4 into 3. So, and it is anti-clockwise, so therefore it is negative. So that is 11.7 kilonewton, and here it should be meter. So kilonewton meter. And bending moment at point B is 0. So bending moment at A is 0. Bending moment at this particular section, that is x, the distance x is always maximum, and that maximum value we have already calculated. The bending moment is always maximum at the point of 0 shear, and that value already we have seen that it is 12.75 kilonewton meter. And as you can see, as it is a UDL, it is a second order equation. So if you remember in the equation, in the previous equation, it is the term x square is coming. So it is a parabolic curve that will always hit. So whenever we are having the UDL, you have to always draw a parabolic curve, and this is maximum at a distance x from A. The moment is maximum at a distance x from A, that is 12.75 kilometer meter. At point C, the moment is 12.56. Then at point B, it is 11.7, and at point B, it is 0. So that will complete our bending moment.